Good. Welcome everyone. TCS seminar at the Jagiellonian University. Today our speaker is Hoang from Paris-Saclay. Hoang is our collaborator, former postdoc. We're happy to have you here and see what's news do you bring. The floor is yours.
All right, thank you very much, Just, for the introduction. So today I'm going to take you through some coloring problems as usual, but from a totally different context than what I am used to, at least. So this project was done with Maxime Flin, a PhD student, I think, who is about to be a postdoc in a way in Local University in Iceland. He's the expert of this local model that we'll talk about, a distributed model of computation. And this was done during his visit at our place in Paris-Saclay, my colleague François Pirot, and then our PhD student Quentin Chuet. All right, so first maybe I should explain what this model is. I will call the classic, say, model that we're working with the centralized model, centralized computation, as opposed to distributed computation. So normally, what are we interested in? So in classic theory of computation, we often think as like one processor, right? We want to solve problems efficiently, such as meaning that the total number of operations is not too big. And sometimes we also care about resource management like memory, right? So everything that we compute in terms of complexity is total number of operations, total amount of memory needed during execution. Right? Now, what is the difference with distributed computing? Well, in the theory of distributed computation, you actually don't care so much about one processor. Now, say that you have a very large network of processors. So this network is modeled by some graphs, right? Not everyone sees everyone. And in this context, we're also less interested in time and memory. So let's say that you have unlimited memory, you have no problem of concurrent access, everyone has their own memory, and you have, in a way, unlimited time, unlimited computing power. So in such a model, what you care about is what we call communication complexity. How many rounds of communication do you need between each of your vertices, so processors in your network, for you to solve a bigger problem on this graph? Okay, so this local model is a distributed model of computation introduced by Lineal in 1987. And let me take you through it like one thing at a time, because I know maybe for some of you this is the first time using this model. So let's take it slowly. First, we have a graph, which is our communication network. Each vertex of this graph is a processor to which we give a unique global identifier. This identifier will be important later on, so do remember this. And there are also some variants of this where you can have like a locally unique identifier, whatever it means. Okay, and the important thing here, why it is called local, is because we have no knowledge about the graph. Say that we have only knowledge of our degree in the beginning, so we know how many neighbors we have. We don't even know the neighbors, we just know how many of them there are. And some variants of this model as well, sometimes called weak local model, you're also given some type of inputs that depends on your problem. Okay, and then recall that we want unlimited memory, unlimited computational power, so we compute everything in constant time, meaning that all of your exponential time problem in this model doesn't mean anything. It's always constant time. Okay. And then the edges between your vertices, between your processors, for today's talk, they will be undirected. Of course, you can also imagine a directed version of this problem, right, where communication can only be sent in a certain direction on both ways. And there's also no limit on the size of a message. If you give a limit on the bandwidth, call it, the size of how many bits you can transfer through these edges, then you get another model as well called the congest model, but this is not the topic for today. Okay, so this is what we have. Now, how can you define an algorithm on this model? So an algorithm, first of all, in this model, everything is executed, every vertex executes the same algorithm. So there's no, hey, if I give some special algorithms to some special vertices on my graph. Of course, you can still use conditionals. Say, oh, if my vertex verifies some condition, then execute this. Right? This is, of course, allowed. So you can still do things for special vertices in a way, but there's no, oh, hey, my algorithm is actually 3 different algorithms, and I give this to these processors and this to another one. Everything executes the same algorithm. And then we don't have asynchronous rounds. Everything works at the same time. Right? Whenever you communicate with someone, so everyone send out messages and receive messages at the same time. Okay. So in each round, what you can do is send a message to a neighbor, receive a message from a neighbor, and of course, do some computations, update something in your own state. And at some point, we have a sort of halting condition. We say, okay, now we're done, and we have to produce some output locally. So each processor produces some output. It's not like a global output on the graph, right? For example, coloring, then each vertex says, okay, I am colored with this color. And of course, we ask for this algorithm to produce a correct output. And this is what we call a deterministic algorithm. We'll talk about randomized algorithms later, where we are allowed to produce some incorrect output sometime, but the probability of error is not too big. Right, so I know this is like a lot of information to take in if you don't know this model before. So maybe let us get another perspective of the local model and algorithms on local model. Okay. All right, so of course the complexity, in this case we care about is communication complexity, which is the number of rounds. So in the local model, there's a certain insistence on locality, right? We have no knowledge about a whole graph, and in each round we can send some information out and receive some information, so we can collect knowledge about the graph, but it stays bounded, right? We have this ball of some radius around our vertex, and after some t rounds, then the most we can know in terms of knowledge of the graph is this ball of radius t around our vertex, right? And also, knowing everything in there, you can also sort of assume that if at some point I have some neighbor in my radius t neighborhood that produce some temporary output during the execution, either you can see it as it has some time to send this message to me to tell me that, oh, hey, I produce some local output here, or you can also see it as, since I have infinite computing power, I can compute myself what my neighbor would have outputted. Okay. So you can see it this way. And what does all of this mean? Well, it means that you can consider an algorithm in the local model just as a function that takes a pair, which is the vertex, then the t neighborhood, like the ball of radius t or surrounding it, and it maps this to some local output depending on your problem. So if you don't want to remember all this synchronous rounds and send, receive message, whatever, you can just see it as you take all the pairs of vertices and ball around these vertices in your graph, and knowing this, you have to produce some output. Of course, the vertices are labeled with their identifiers. Okay, so this is another way of seeing what an algorithm, a deterministic algorithm is in the local model. And now let us talk a little bit more about hardness. Right? So we're measuring in number of rounds. So what does it mean for a problem to be hard, right? Or what does it mean for a problem to be easy? So since we have unlimited computational power, of course, if I have number of rounds, diameter of the graph, then I can know my whole graph, right? And once I know my whole graph, well, I can compute anything I want, and so I will know what my own local output is. So algorithms that take number of rounds linear in number of vertices, or at least the diameter of the graph, are not very interesting. This is sort of the equivalent of kind of taking exponential time, right? In the centralized model, when you just naively run through all the solutions, for example. Okay, so remember that, yeah, linear is very bad. So we're only dealing with like very, very small quantities here. And there's also this sort of lower bound notion of what we call inherently non-local problems. I think you can get this feel that, okay, since I only know a ball of radius t around my vertex, there are some problems in graphs where, yes?
Does the vertices know the total number of vertices?
I don't think so, at least not in this model that I introduced, but yes, sometimes there are some problems where they can consider, okay, this is like part of the initial input, for example. Yes, so inherently non-local problems, well, what does it mean? It means that if somehow there is a vertex that is very far away from me, like further than what I can see, basically, if this vertex has to change its output and it has influence on my output, then this is inherently non-local. Because during these t rounds, I cannot get this information. Now, this seems a bit abstract, I guess, so let us take a very concrete example, and a very simple one as well. Two-coloring of a path, right? This is very easy in centralized model. Just testing if a graph is bipartite is also very easy, right? But this problem is like an inherently non-local problem. Now, why is that? Okay, so maybe let me, oh, sorry, I forgot something. Let me show you maybe something easier first to just get a better feel for local algorithms. Okay, so before going to two-coloring of a path, let's just take some graphs and see how we can execute a local algorithm on this graph. So here, I want to talk a little bit about coloring first. Okay, so this is my graph, and these are my identifiers. Okay, and I just want to apply a very simple one-round greedy coloring algorithm on this graph. Okay. So greedy coloring here means that I always choose the smallest color available. In the centralized model, this is pretty easy, right? You just look at your neighbors and you take the smallest color available to you and get some proper coloring, right? Okay, so what happens here if I just look at my radius 1 neighborhood and try this greedy coloring algorithm? So 3 here sees 12 and 43, right? And I say that I choose my color first if I have a smaller identifier. So this will get color 1, this will get color 2, and this will get color 1. For example, this here will get color 2, right? It's these two guys. It's like the second smallest. 2, this here, it sees all these 4 guys, and it's like its third smallest, so it will choose 3 here, so everything is fine until now. But when this sees its 2 neighbors, it will think, okay, this one is the smallest, and then this one, and then there's me. So I probably choose 3. Okay. So this is just to showcase like a simple algorithm on this local model. Just I look at my neighborhood because you have to imagine that all this is going on at the same time, right? It's not like, oh, hey, I know that this guy chose some colors before, and so I can choose another one. It's not true, right? All I see is this. Yeah? I didn't know that there's some other vertices over here. Okay. So even like something very simple like this, right? It fails miserably since you have to sort of do it all at the same time, not sequentially. Okay. And just like a remark, by the way, since we have unique global identifiers, sometimes you can use this as a trick to just say, oh, hey, if I just want to produce some proper coloring of my graph, then I can do it in 0 round. It's just take my identifier and output it directly. All right, so now let us move on to coloring of the path. Why is this inherently hard in a way? Okay, so let's just think of a very long path. Okay, and let us assume that there is some sublinear algorithm that color my path. Okay. So what does it mean? It means that, for example, let's take this vertex. It only sees this part of the graph, okay? And it has to produce some output. The same for this one. So let's highlight these 2 vertices. Okay. Since this is a 2 coloring, if I have 2 vertices at even distance, then they must have the same color, right? So here I would expect some output like 1, and it's 2, 1, 2, 1. So imagine that we have some algorithm that can output this kind of thing, right? Well, now what is the problem? Well, the problem is that if I remove this vertex now from my path, then my algorithm, which is the mapping from this neighborhood to a local output, see the exact same thing, right? In both of these balls of radius t. And so I'm supposed to still output 1 here and 1 there, but now the distance between these 2 vertices is odd, right? So I'm not supposed to have the same color. Is that clear for everyone? So this is like one of the, say, the techniques for lower bounds in this sort of model. Okay, so yes, you remove this vertex that is outside of both of these neighborhoods, and then you obtain some contradiction. All right, so let us move on to, I hope that you understood algorithms in local model now. So now I want to introduce randomized algorithms. So what are randomized algorithms? The idea is, yes?
Sorry, referring to this, like, can you get a better algorithm if you want 3 colors rather than 2 colors?
Yes. Actually, I will show 3 coloring like right now, but a randomized version.
Not randomized.
Yes, there is a non-randomized version of it, but that I will not show. But okay, yeah, there is one. I will talk about it just in a second. Okay, so let's take randomized algorithms. So everything is the same as before, with the exception that the ID are a little bit different. They are randomized, but over infinite bit strings. Now, why the reason for this? Well, some algorithms rely on this part of randomness to produce some results, because in the other case, you can see these global identifiers as arbitrarily chosen identifiers. Yeah. You don't want to rely on them to produce your deterministic results. Okay. Like, for example, you cannot assume that your path is like labeled 1, 2 to n, right? For example. But in a randomized setting, sometimes some algorithms rely on these randomized ID, and so we also do not want an adversary to choose a very bad case for our randomized algorithm, which will always produce like incorrect results. Okay. Right, so the random part of this is for any constant C, you want your algorithm to be able to produce correct outputs with probability at least 1 minus 1n to the C, 1 over n to the C. So you can get as close to probability 1 as possible. Yeah, so when we say there exists a randomized algorithm with so-and-so complexity, is that it produces very good output for any like epsilon, as close to 1 as you want. Okay, so let me show you a very simple way to 3-color a path or even a cycle with this randomized local algorithm. Okay, so let's take this. Maybe I can draw it below. So we start out with a rather simple coin flip. Okay. And then, let's say that some of these get color 1, say this one, these 3, and then maybe this one. Okay. Now, what you want to do next is that you want to remove all the monochromatic edges, I mean the color on both ends. So this one has no neighbor colored 1, so it keeps its color, that one as well, and all of these guys will get removed. Okay, so let's remove these colors. Okay, so now what I want to do is I want each of these vertices to sort of explore this path. Right, so I will just look at the colors of my neighbors until I reach someone colored 1. Okay. And once I've done that, then let's say that this one has ID 42, and this one has some ID like 77. Then I have to choose one of these two guys to take care of the coloring of this path, basically. So let's say that I chose the smaller one. So this one, it will just say, okay, let me 3-color this path, something like 2, 3, maybe 1 here, 2, 3. And then I have some sort of halting condition, like, okay, if I do this for too long, then maybe I stop before and I say, okay, sorry, I failed. You know? Because you can imagine maybe in some cases, like somehow a lot of vertices are not colored, so you have these very, very long paths between two vertices colored 1. Now, let us try to analyze this a little bit. So what is the complexity, communication complexity here? So each vertex is colored 1 after the first round with probability like 1/8, right? You just, for example, you take this guy, then it stays with color 1 if it had chosen color 1 first of all. So it's 1/2, and these neighbors must not have chosen color 1, right? So 1/2, 1/2, and so this gives you something, a chance of 1/8. Now you want to compute what is the probability of having a lot of consecutive non-colored vertices between two vertices colored 1. Okay. So let us first just look at what is the probability that, say, a triple is non-colored. Okay, so I will say that this is 1 minus the probability that at least one of them is colored 1. I mean, one of them in this triple. Okay, since I know that this is at least 1/8, right? We have this is at most some constant less than 1. Okay, and so using this now, I can say that the probability of no vertex is colored 1 in some L consecutive vertices is at most, well, I just take them 3 by 3. Yeah? 7/8 to be L/3. Okay, and now this here, I'm taking it to be log n, about log n. Right. So this square will depend like on the constant c that we talked about earlier. And now if I do this, and you can compute this, of course, which is should give you something like 1 over some polynomial of n. Again, this depends on c. So for the carefully chosen L, you get the probability of error as small as you want. So you're sort of sure that this halting condition that says, okay, I need to stop after some point is okay. And most likely you'll be able to discover your path between these vertices and free color your path. And yes, there is a better deterministic algorithm for tree coloring, and actually for constant number coloring in log star and rounds. Where log star here, you recall that it is the number of time you need to take the log from n to reach something like n-2. And okay, I'm not going to show it, but the idea is actually this thing I mentioned where at first you consider that your color is your ID. At least you know that everyone will have the same color. And then there is like this iterative procedure that is applied where every time you try to reduce the number of color used by looking at your neighbors. And so at some point you manage to take it to a constant number of colors. And there's some inequalities that you need to verify, which guarantees that this constant number must be actually bigger than 2. But okay, I'm not going to show this proof. And actually, it was also shown that there's a lower bound for this. And that's, you cannot do better than log star of n. And even better than that, the randomness does not help at all. Meaning that you have also theta of log star of n for randomized algorithms. All right. So now that you sort of understood what the local model is, I will talk about the second part of my title, which is non-repetitive coloring. And actually, I'm going to consider a whole class of problems of colorings from the perspective of forbidding some patterns on some paths, or sometimes cycles. So what do I mean by this? For example, if you can take a look at proper colorings, well, proper colorings can also be defined as colorings such that there are no path on 2 vertices, such that you have the pattern 1, 1. Okay, 1 here is just a substitute for some arbitrary colors. Yeah. So you take any path on 2 vertices, you never repeat the same color. You can think about distance coloring. So what is distance coloring? You forbid pattern 1, 1, right, in your immediate neighborhood. And if you have some path on 3 vertices, then you sort of don't care what is the color in the middle, you want to forbid that the two ends have the same color, right? So you're forbidding 1 to 1, for example. You can also think about, okay, another version of this, injective coloring, is when you don't have the same color as someone else if you share a common neighbor. Right? So this is the same as forbidding just 1 to 1. This can be an improper coloring. You can also think about star coloring. Star coloring, what is the definition? Well, when you take any, first it is a proper coloring, and then when you take the union of any two class of colors, you get a forest of stars. So actually by forbidding 1 to 1, 2, for example, you can achieve this. More examples, cyclic coloring. So proper coloring again, and union of any two class of colors is a forest, so no bicolored cycles. Right? And then the one we're going to talk about today, non-repetitive coloring, which is I take any path and can see it as a word, let's say, right? Where each color is a letter, and then I want my word to not be a square. Right? I don't want it to be the repetition of the same sequence of color. Why? That's why it's called non-repetitive coloring. And why are we trying to solve problems for non-repetitive coloring in this case? Well, because all of these colorings that can be seen from this perspective of forbidding patterns on path, we can use sort of the same ideas and techniques, same box of tools to get very similar results. So our hope was that by working with non-repetitive coloring, which is in a way the hardest of them all, right, with a lot of constraints and arbitrarily large constraints, if we manage to do it, then our hope is that we can translate all of the things that we know for these type of colorings on normal centralized model to the local model. All right, so now let us just forget everything and think about non-repetitive coloring, and even better than that, square-free words. Okay. So non-repetitive coloring is defined for graphs, right? You take any graphs you want, take any path you want, and you need to forbid these patterns. But now I'm just going to talk about paths, one-dimensional graph. Just so we get square-free words, that do not contain squares. So what do we know about square-free words? This is a result that exists from quite a long time ago, which is an explicit construction on 3 letters that gives you arbitrarily long words without squares. And in 2007, it was conjectured that you can actually do a list coloring version of this. And what does it mean? It means that you have a sequence of lists of size 3, each of them, and you want to build a word such that each letter is chosen from the corresponding list. And again, for this word to be square-free. Okay. And this conjecture is still open, but there have been many results, actually, showing that if you move this bound up to 4, then this is true. If you have lists of size 4. And this has been proven many times. I think the first proof was 2011, using some variant of Lovász Lemma, which I will talk about right away. And then entropy compression 2 years later. Again, and like say an algorithmic constructive results, very close to the idea of Lovász Lemma, which I will also present. And finally, very recently, Rosenfeld counting from Mathieu Rosenfeld in Montpellier. So what is new with this proof is that not only does it give you existence of square-free words, it also gives you the number of square-free words that you have. For example, right on a list of size 4, a number of square-free words like that. Okay, so let me give you a tour of all of these proofs first. We're talking about existence proof here, right? No local model, no algorithms yet. So maybe first let me recall Lovász Lemma. Maybe even the symmetric version of it. that you might have seen in school. So what is this lemma saying? The idea behind this is actually pretty straightforward. Well, let me call it symmetric. You have a set of bad events, or whatever bad means. And they all occur with probability, let's say, at most p. Also, you want each event to be independent of all others except for d of them. Okay. Now, if you have such a collection of bad events, then for the right condition on P and D, E here is like the normal E, right, like 2.72 or something. Then none of these occur, so let me just write it like this, with a bar here to say that it doesn't occur, with non-zero probability. So how do you use this sort of thing? So you can think about it like, hey, I want to produce some colorings on my graph, right? And I made some random choices. The bad event is just that I don't produce correct colorings. And if I can do two things, so bound the probability of such bad events and also their dependency, if you think about it like, if all these are independent and none of them occur with probability 1, then you can sort of just use this independent hypothesis to conclude that I can avoid all of them with non-zero probability. Right? So Lovász local lemma, all it is saying is that it's the same idea, but we allow some dependency between the events. Not too many of them, though. And this is why we have this. Okay? So this is probably the version that you've seen. Now, actually, to prove something for non-repetitive coloring, I will use a more generic version of this, or a stronger version, which is the asymmetric one. You still have the same sort of set of bad events, but now instead of having the same bounds on the probability of everyone, you have these coefficients, these xi's. You can think of them as like being very close to the probability of bi. And so if you can bound this probability by something that looks like this, there's some dependency that appears here, then you can avoid all of them, once again, with non-zero probability. Okay? So let us try to see how we can use this in our problem. So for non-repetitive coloring or square-free words, first, you just do a very naive choice. Take your list of colors and just take one uniformly at random. What can go wrong? Well, the thing that can go wrong is that, of course, you created a square, right? So I'm going to define this collection of bad events, which is BIL. And what I'm going to say is that basically there is a square that starts at index I and it's of length 2L. 2L because the square is a repetition of a word. We can easily see that these are not independent if these indices overlap, right? You sort of have this interval in your word, and if the intervals covered by two different bad events overlap, then there is some dependency between them, right? If they are on completely disjoint set of indices, then they are independent, right? So now to compute the probability of the IL, then what do you say? Well, what does it mean to have a square? Well, to have a square, it means that you have these L pairs of vertices that somehow chose the same color, right? For two vertices to choose the same color in list of size k, it's just 1 over k. And these choices are made completely independently from each other, so it's just 1 over k to the L. Yeah? Just probability of BIL. Now this part is easy. Now the next part is, how do we choose these coefficients so that I have this inequality? Now here, I'm not going to enter into the computations of this thing, but all the ideas are here. Yeah. You choose these XIL to be sort of close to the probability of BI. Here I didn't even put like a constant that is like that depends on your position. Say you take the same for everyone, right? You can be more precise in this. And you sort of have this bound on the dependencies between your events just from this observation that these intervals overlap. Yeah? This gives you on like the maximum number of events you can overlap with. Right? And so if you just choose these carefully, it works for like k at least 8. I think like if you choose it very carefully, it might work for k's at least 6, something like this. Well, what I promised 4, well, this is sort of like a simplified version of it, because the proof with 4 did not use this version of Lovász local lemma. You might have heard or seen like there's a whole bunch of different variants on LLL, and so this is like one of the simpler ones. But the ideas behind it stay the same. If you take some other variants with more involved conditions and you do a better analysis of your events, of the dependencies between them, then you can get better bounds. Now, I want to talk about something that we call algorithmic LLL. The thing that I just presented is a non-constructive proof, right? Just existence. But somehow there's this idea behind it, which is very natural and which is algorithmic. This analysis seems a little bit hard, but what did I do? I just took a choice uniformly at random, and that's all I did. Right? Then the analysis is the complex part. So what if I can use this idea to say that if I want to produce some coloring or some square-free words, then each position just needs to choose a letter at random, right? And if it doesn't work, then somehow I need to resample it. But there's this algorithmic idea that is hidden behind LLL. Right? Okay, so yes, classic LLL is non-constructive. And actually, it took quite a long time. So in 2010, Moser and Tadeusz showed very famous proof now that the idea that we just mentioned, this very naive idea of just doing a thing naively, like taking something at random, works. So for every random variable in all of your path here, you just pick a value randomly. Maybe you have some more involved probability distribution, but most of the time, actually, for the proofs that we know, we actually just pick uniformly at random. And then, while there is a bad event that occurs, then you just delete stuff and you resample. You have to be a little bit careful about it. You don't want to delete everything. You just delete the minimal amount of things that trigger this bad event, right? And just resample that. And you just do this until it works, basically. So this very simple algorithm actually is the answer. This is what algorithmic LLL is, and it took quite a long time actually just for the analysis of this algorithm to show that doing this you can get the same bounds as the classic statements of LLL that we see. And the good thing about this is that it's very powerful in distributed model as well. You can adapt this pretty easily to the local model. And the only extra step that you do is, well, in this version of algorithmic LLL, you can think of it as, okay, everything picks something at random at the same time, right? And then you solve bad events one at a time. Yeah. Say, okay, there is some bad events here. I take this, resample what is necessary. I fix that. Okay. Oh, there's some other bad events here. I took that, resample what is necessary. I'll fix that as well. Right? So how do you distribute this? Well, it's very simple. Just take a maximal independent set of bad events. Yeah? Bad events that are on variables that do not depend on each other. You can do them all at the same time, right? So this will save you a lot of time. And this is where this sort of complexity comes from, is the time to compute a maximal independent set on this sort of graph of dependencies between your bad events. Okay. So you have to be a little bit careful with this term, though. Right? This doesn't mean that it is O of log n. If this thing is very close to 1, then this log thing can be very, very big. Right? So this is not the end of the story. Well, it was later also improved a little bit to remove this log n here in the complexity in exchange for something that depends on the dependencies. Okay, so I hope that it was clear for everyone. Now, let me talk about some other, let's say, version of algorithmic LLL. When this paper by Moser and Tadeusz came out in 2010, or actually 2009, published in 2010, Terence Tao coined this term entropy compression in some of his blog posts to talk about this. But nowadays, actually, we think about entropy compression as like a sort of different class of algorithms, very similar to algorithmic LLL, but nonetheless different. And it works at least as well, and most of the time, actually better. So what is entropy compression? Let us again take the example of square-free words. This time, instead of doing all at the same time, right? Remember algorithmic LLL, every vertex pick a color all at once. Let us do it sequentially. Let's say from left to right. Okay? I start with the first vertex. I pick some color uniformly at random in, say, my list of size 4. And if I didn't create any square, I just continue to do that. Okay? So same sort of idea, just picking uniformly at random and just doing it as long as it works. And then if it doesn't work, then same idea again. I just delete just enough so that it's still a square-free word. Okay? And what it means just enough in this case, well, if I have some square, then I delete the second half of it. And we try to make progress like this until we hopefully reach the end of this word. Okay? So let me run an execution of this algorithm with you, just so that we're sure that everyone understood what was going on. Okay, so let's follow this algorithm. And say that I start with something like this. Okay, I chose color 1, then 2, then 3, then maybe 1, 2, and 3 again. Then I found a square, right? So I delete the second half of the square to get 1, 2, 3. And then now I start again. Let's say that I did 1, 2, 3 already, right? So now I have a 2, maybe a 3 again. Oh, I created another square. This time, half of it stops here, right? 2, 3, 2, 3. So I delete it again. And then I continue. Let's say it's 1, 3, 2, and so on. And I do this until I hopefully reach the end. So how can you show that this sort of algorithm actually ends, right? Because it needs to end for you to show that this is possible. Well, this is this idea of keeping a log of your execution. So you want to produce a log which is just the minimum amount of information necessary to encode your execution. And in some way, if you have a good control over the number of possible logs, and that it grows slower than the number of possible execution, then at some point you know that there's no execution that can be too long, right? Because there's no way, there's no other possible logs for it. Okay? So what kind of log here we can keep for this? Here I call it like something of a die path that is equals to the length of the word we have currently, and also I keep the color of the current word. So what does this look like? Let me write the log for this same execution. Okay. Okay, maybe. Right. So if I just start with this, right? So I managed to get the column: 1 guy, 2 guy, 3 guy. I even went up to 6 guys. So 1, 2, 3, 4, 5, 6, and say this is my baseline. And I deleted 3 of them, right? So 3 step down. Managed to generate 2 guys. Unfortunately, deleted both of them. And then now I just managed to generate some more. Okay. And let's say that my execution stopped here. And what are the colors that I have? I will write them like this: 2, 3, 1, 3, 2, 1. Sort of align with these levels. Okay. So this is my log. I have some colors. I have some die paths encoding the lengths of these things. Now I want to show you that from this log, I can recover my whole execution. So that it really is like a one-to-one mapping. Okay. Right, so how do I do this? To recover this execution, I'm actually going back in time, starting from the end. Right? So I'm here. I have some path going up. So I know that on the previous step of this execution, I did something like this. I had this word, right? And then the one before that, I had this word. Okay? And then the one before that, I had this. And now I see that I have some path here that was going down. So from this, I know that I deleted some squares, right? And what is the length of this square? Well, I see that this path that is going down is going 2 steps down. So the square must be half of the square, right? It's 2 letters, so it must have repeated these 2 letters. Yeah? 2, 3. So yes, so before that it was something like this, and now I do the same thing again, right? This was 3, at this step this chose 2, and now all this is going up again by 3 steps, which is also a square, and it's length 3, so I repeat these last 3 letters. 1, 2, 3. And then once again, from this point on, it's easy, right? You just go down the line, and then you know that the sequence of colors generated was exactly this one. Okay? So this execution, how do you think about it formally? Well, it's just at each step, you're making some choice of color between, like in a list of 4 colors, right? So how many possible executions you can have? 4 to the t. Now, the number of logs here is a little bit less than that. Well, how can you see this? Well, this thing that you keep at the end is at length of at most n, right? So each of these can have up to 4 different colors. So you have 4 to the n here, and then the whole thing here was sort of like a partial die path. You can think about it as you can complete the end of this to get a real die path, right? Just doing the step downwards until you reach the end. And so you get some dyke path on like of length 2t. And this is some Catalan numbers, and if you estimate the asymptotics, and you'll see that this combined with this, at some point, it cannot grow as fast as 4 to the t. That's basically it. Remember, this n is fixed, whereas this t can be very big. Yeah. So basically, at some point, there are no executions that can last that long, because we're encoding these executions with these logs that are one-to-one mappings. Okay? So this is just some clever counting tricks to show that this algorithm must end at some point. Yeah. And remember, all we did was we choose our colors randomly, one at a time. Not all at the same time, just one at a time. And then we delete things the moment it goes wrong. Okay? And just this little improvement actually gives you, most of the time, better bounds than normal classic LLL. It's sort of intuitive in a way, because in algorithmic LLL or classic LLL, you do a lot of things at the same time. So a lot of things can go wrong as well. Here you're just doing things one at a time. You build your coloring sequentially, but the moment something goes wrong, you delete it, and what you get is something good. Whereas doing a lot of things can create a lot of problems. All right. And the nice thing about this, I'm not going to prove this, but that the expected running time of this algorithm is actually linear. It's actually rather efficient. So not only that we get existence, we also have a very efficient algorithm. And all of this for now in the centralized model, right? You can see that I cannot just apply this directly in the local model, because if I just do things one at a time, then and with a communication complexity of n, I could have solved anything, right? Okay. So lastly, I want to show you another proof of this thing, this time with this Rosenfeld counting that we talked about. This is arguably the simplest proof of them all, but it lacks the constructive part. But we also gain this enumerative part. You know, we can count the number of good colorings or a number of square-free words. And actually, I like this counting very much, because it's so easy, it's so efficient, that whenever we encounter some sort of problems that we know can be dealt with LLL, then the first thing we do is Rosenfeld counting. It takes like half an hour, and it already gives you, most of the time, very good bounds, like probably as good as you can hope for with some very involved like variant of LLL. Okay, so what does it state? Here I'm going to state a version of this which is a little bit more informal and only for coloring, but there's actually like a formal framework that was introduced for this. But in practice, this sort of statement is pretty nice for us to use. So what does it say? I have some number of colors. I want to count this Tn, which is the number of what I call good colorings. It depends on our problem. And I claim that it grows exponentially fast with this growth rate of beta, as long as beta verifies some equation. So this is most of the time what we're relying on. So if we adapt this for our problem, what happens? Let me check the inductive case first. So we're proceeding by induction here. I'm just going to assume something like Tn is at least beta to the I, Tn minus I. It's like strong recurrence. And how do I count Tn plus 1? Well, what I say is Tn plus 1. So square-free words now. Think about square-free words on n plus 1 vertices. Yes?
What do you mean by beta is nice?
Yeah, so it will come. It will come in just a second. Yes. So beta will have to verify something, and that thing will come. That depends on our problem. So it will come here. Yeah. Okay. So in square free words, if I delete the last letter, then the n first remaining one is also square free, right? So I can see Tn plus 1 as some sort of extension of Tn, right? So I took like a good square free word, Tn, and then I added some letters at the end. How many ways do I have to extend this? K, well, or 4 in this case. But, of course, maybe not all extensions work, so I need to remove the bad ones. Okay? And not only for square free words, like a lot of problems can be think about this way. You want to count something on n-1 vertices, for example, in your graphs, let's say, to produce good coloring. Well, you take a partial coloring, which is good for n vertices, and you extend it with some number of colors. Yeah? And then you remove the bad ones. So up until now, actually, this is sort of like a very generic way to do things. Now, how do we count this? Well, this, of course, will have to depend on our problem. What can I say is actually the same reasoning as entropy compression. Okay? What can go wrong? Say I add some letter, right? I created a square. Then I just delete half of this square. What remains is a square free word, right? So it is counted in this number of like Tn plus 1 minus I thing. And there's exactly this many bad colorings of them because I know that, oh, the square was length 2i, so it repeats the last I letters. So I just need to complete it to get back my bad coloring. Okay? And I sum this for all possible values of I. Yeah? So this is the part where it will depend on our problem. But up until here, it's sort of like a generic framework kind of way. Now, everything is super easy, right? Because I have this assumption, which replace this, and computations, and so on. Right, so I have some geometric sum here. I'm just going to bound this by like an infinite sum. Okay, so I get something like this. And now, what does it mean to be nice? Well, it means that here I need a solution. I need this to be like at least beta Tn for it to work. So nice means just beta verifies this equation. And where this equation comes from? Well, it comes from this counting for our problem. Okay. So it's a bit hard to write it in a formal manner, but this is the idea behind it. And you can check here that beta equals 2 is like the only solution to this equation. And of course, you can check that the base case work as well. Of course. Right, so that's it. So in the span of like maybe 3 minutes, we reprove all the same things that we did before in a much simpler, much faster way that somehow gives also the number of such things. Yeah. Now, all of this is very nice, but I still haven't talked about anything new here.
So the reason why the previous slide, the first inequality, it's an inequality and it's not an equal thing because when you start to build repetitions, you could create a smaller repetition, and that creates. So that's why it's not.
Yes.
This would be very crazy if it would be tight.
Yes, but it is not tight. And actually, this is like one of the first version of this thing. He proved that you can improve beta to, I think, 2.5 or something like this. So and then he also said in that paper that with the help of some computations on smaller words, you can probably improve this beta as well. Yeah, so we're still pretty far from this being time. Okay. Right, so all these tools are like great. It's very nice for centralized model, but how can we sort of use them for the local model? We already seen this algorithmic LLL that was adaptable to the local model, right? That we can distribute. Do all of these like solve all these bad events in a maximal independent set of them at the same time. So our hope with this project initially was that maybe we can have also an equivalent version of entropy compression for local model. So instead of doing everything at the same time, you're sort of doing things one at a time. So you have some uncolored vertices in your graph, you build things in a way by batches, and hope that there's not too many problems. Now, a little bit of a spoiler here, it didn't work. Now, what does it mean that it did not work? Well, if I translate this very natural idea, which I will talk about right away, well, you can actually get results for a local model. You get real bounds, you get real proofs, algorithms, and so on. But these bounds are rather bad compared to what we can get in the centralized model. So in that sense, it is not as interesting. Yeah. If it's worse than what we can obtain with LLL, then what's the point, right? Okay, so let me explain now what I mean by the natural adaptation of entropy compression.
Just local lemma, you get very bad solution, right? You have potential huge events, global events.
Yes.
So if you just apply local lemma, you already get something that is not useful. You expect some kind of logarithmic, polylogarithmic at
yes,
number
yes.
of steps, right?
Yes, yes, yes.
So local lemma doesn't give it, so.
Well, depends on. Well, actually, most of the time it does work, but of course it depends on this EPD thing, and this adaptation. This idea of distributing it with multiple, like solving multiple bad events at the same time in this maximal independent set is actually enough to reduce the running time.
The question should be, what is your graph of processors? Is it a path or is it a dependency graph of the problem?
Yeah, so actually you're solving MIS, maximal, not maximum, on the dependency graph, but you can use this to solve problems on your graph. I know it's a bit weird, but yeah, this adaptation to the local model actually works in a lot of cases. But yes, it's we were hoping for entropy compression to work, and in a way, it's much simpler as well. Like with when you don't have to work on this dependency graph, because sometimes you just don't know what it looks like, and it's very hard to bound this this quantity, this EPD. Okay, so what is like a natural way to do entropy compression? Well, entropy compression, you're sort of doing it in n batches of single vertices, yeah, sequentially. What if you can group some of these execution together and do them at the same time, right? So the idea here would be to first color your graph. So this is not the coloring that I will keep in the end, but just like some pre-coloring so that I can divide my vertices into batches. And what are these batches? Well, for now, I take some log n distance color of the path. So you can think of it as you just take the power graph of this path, right, up to log n, and then you find some proper coloring. So this can be achieved with some 2 log n colors. And now I will execute entropy compression for each classes of colors. So instead of having n batches, I have about 2 log n batches. Yeah? So the idea is that in the end, instead of having something that is expected linear time, I have something in like log n time. And now these n batches, what are they going to do? Well, at each step, they do exactly what they would have done in entropy compression. Choose a random color from the list of size k, and then after each round, they look at the ball of like radius log n around them, try to see if there's some squares there. If there are some, then you just sort of erase half of them. Now here, since there are no like direction to this path. Yeah, and I have to imagine that I'm some vertex in the middle of nowhere. I don't know which way it goes, so there's no second half. But I can just rely on my ID to say that, okay, what is a square? A square is some number of pairs of vertices with the same color. So for each pair, I just remove the color on the bigger one. Okay, so this is also deleting sort of half of this square. And since I only look at this log n bold surrounding me, I am independent with all the other guys doing the same thing at the same time. Yeah. So in a way, we want to distribute this to parallelize this, but we also don't want it to interfere with each other too much. And then, actually, that's it. Yes.
So how do you get this log n distance color?
So here we just actually apply some known results for just delta plus 1 coloring but this time of the path like to the power log n. So you take the same algorithm, you just multiply it by log n because you need log n rounds to travel like one step, right? So if you have some efficient algorithm for just normal coloring, delta plus 1 coloring, then you can use that. Just do it log n times slower.
And the number of rounds there is what?
Yeah, so this is what I wrote here. I didn't write down the exact thing. There are multiple results for this. Also, it depends on the regime, meaning like if how large is delta compared to n, and depending on this thing, they have better algorithms with different complexity. Yeah, delta. I mean maximum degree. You take this power graph, right? And the maximum degree is will be like 2 log n or something. Yeah.
Okay, so there's a 2 log n coloring.
Yes, of this graph, and maybe you can aim for something better because you know that is the path. I just took the result from general graphs, and I think there was some log square delta in there, something like this.
So it's
and then plus log n.
It's just like an improvement.
No, I'm sure it was improvement to this polylog. For a long time it was known to be polylog.
Yeah. Yes. Yeah, yes. In general, I think it's log delta, something that was known. Okay. Yes. So here we're just taking something known and then use it directly.
So log would be, this is poly here.
Yeah.
Log would be better, right?
Yeah, but because in this thing I have to multiply by this log n already, just to see as far as because you're not calling your graph directly, you're calling this power graph, right? But you cannot travel as fast. You don't have these edges for real.
True.
Yeah. So you're already multiplying by log n. So this part you can't really save here. Okay.
You pre-color this?
Yeah.
Sorry, because I got stuck at the first item.
Yeah, well, I mean, maybe let me try to do something.
Can you do random?
Yeah, so really the idea is just to take this pre-coloring and then do some stuff at the same time. The rest is, we rely on entropy compression. So you have this super long path, right?
Okay, but the graph for the local computation loss is the top now, right?
Yeah. I'm just looking at the path.
And then each vertex gets an input, gets its list. Yes?
Yes.
Okay.
So let's say that this X is like one class of color. We have some O and squares and triangles and so on. The only thing I'm asking for here is they are sort of far from each other, meaning that these things that are colored the same, they are distance at least log n. So say that you have some ordering, right, on these things. Let's say that X goes first, and then, I don't know, this triangle, and so on. Okay, and then you repeat. So what happens here is like these guys choose some colors, and then those other guys choose some colors at some point. They see that in these sort of balls surrounding them, these do not touch each other. That maybe in this one, let's say, maybe let me move a little bit over here, it found some squares, right? Something like maybe 1, 2, 1, 2. Okay. So what it does is it looks at the ID of, let me space them out a little bit more, of the vertices corresponding to it. And this was 10, 77, 43, 42. Okay. Now, for each pair of the same color, say, oh, which is the one with the smaller ID? So I don't remember which one I kept. So I kept the smaller one. Okay. So for this pair, you remove this guy, right? And then for this pair, you remove this guy. Okay. So yeah, before we had like a direction, right? We say we go from left to right, remove the second half in this left to right thing. Now we're just saying, okay, you look at the IDs and you remove the half that has bigger IDs. Okay. Otherwise, it's really the same idea. And now, here instead of having one log, we are sort of having like some information kept here. We have these log n logs. And in each one, we sort of the same idea of we want to keep something that indicates what was deleted. And then using the current coloring, you can recover this lost information. Okay, here I'm not going into details because we try to go to the end of this and then find out that the problem is not here. The problem is much more fundamental. So let's say that everything here works fine, yeah, somehow. But yes, just the same idea. You kept the minimal amount of information possible, and then you can recover this information because you have this procedure. You also parallelize, like distributed this sequential algorithm in a way that you guarantee you don't have too many rounds, right? Instead of n batches, you have log n batches. So yeah, so the expected thing here would be some log n that will enter this polylog n. Right? From step 2 onward from entropy compression. Yeah? So before n batches, this time log n batches. Even the correctness can probably work, even though it's really hard to analyze here. Here to analyze, like, did you create a square somehow? Yeah, it's pretty hard, but the same idea behind it is, why did we take log n? Because in this log n radius, we avoid small squares. Yeah, there are no small squares in this log n radius, and we wanted to say that if there are long squares, then the probability of this happening is exponentially small. Okay. I'm not saying that it's hard to, it's easy to analyze this. Like concretely, when we try to go to the end of this, we had to introduce more randomness somewhere.
Because by resampling, you can create some correlation. This is not trivial at all, I guess.
Yeah, this is very, very non-trivial. But let's just even assume that we don't know how to do it, but that it morally works. I want to go to the next point, which is, even if all these things that are very complicated could work, we have a very big problem, which is hard to sort of formulate in words. But this problem, I think, is like the same idea of how entropy compression managed to do better stuff than LLL. Because LLL, you do everything at the same time, you have problems sort of everywhere, it comes from everywhere. In entropy compression, this going from left to right thing actually really is very nice.
But this was also the trick proved by Yannick and
others of this group, because their version was left-handed local lemma.
Yes.
So also local lemma, so there are 4L, and there was also this global direction.
Yes.
Which I guess is in the spirit of what you say.
Yeah. So this attempt to sort of do a lot of things at the same time means that just even on the path, your squares can be created both ways, in some sense. Yeah. It can come from some stuff that was from the left or some stuff from the right. And actually, this 2 really does appear in the calculations. Like if you really try to compute this, then this 2 appears and it stays. So we almost get twice as many colors as we would need in the centralized model. And this is like rather bad, from 4 to 8. So there's this dight path thing. You see that maybe you can analyze it a little bit better. In this case, it's not exactly the same thing.
Do you have an arbitrary constant in the local model, like a constant? That would be a first question. Yeah?
Oh yeah. So okay. So I will talk about this in a moment. So
but what if you had a directed path in your local model, so that you actually can delete the second half always because you know the direction?
But you
Does
still
it change anything? Or?
So we also thought about this, but I mean, we don't think that it changes anything because you still need to do some stuff like sort of on your right at the same time, right? If everything's happening is like happening on your left, then how do you like sort of parallelize this process? You see what I mean? Like you can, sure, it helps you with like this sort of thing. For example, you can say, okay, now I have a real definition of second half depending on this direction. But the problem is not really there. The problem is that since you're coloring some stuff over there as well, and there's some maybe uncolored stuff in the middle, once like these 2 like touch each other, you're like, oh, problems from both sides. So yeah, we haven't really found a really like a nice way to adapt this entropy compression, and somehow it feels like almost impossible. I wouldn't claim that it is impossible, but this thing of having to do a lot of things at the same time, a lot of things happening in your graph, makes it seems like it's very difficult to do this. So we just try to not do entropy compression and just do some ad hoc algorithms directly and using 4 colors actually. So our result is that there is a randomized local algorithm in some weird complexity, and this is not because really of what we do specifically. We're just using some other known result as well, known other algorithms, and this gives us something that is basically this is like a big old log square.
So now there are no lists, right?
Oh yes, okay, and yes, in this version there's no list. We just prove it with one color 1 to 4. Yeah, if you're interested, you can think about like a list version of this. Okay, and we also have some other results, but this is still an ongoing project, so I'm not really going to talk about them. Now I'm going to show you this, but maybe first let me claim something. This part is not really interesting, so let's just assume that we have this. That we can construct square-free words, but also they start and end with the same letter. This is just some manipulations of explicit constructions. Actually, the 2 more sequence. Yeah. So let's just assume this part is like just some explicit constructions with some arithmetics. Okay. So let's say that we can do this. Then what is the proof? We again fix some length, which is log n. This trick really seems to work very well in local model. And the first thing that we are trying to do is just cut up this path. Do this here. Okay, so imagine that you have some super long path again. This time I just want to cut it up some points here. 1, 2, let's do 4. And what do I mean by cutting it up? Well, I'm computing some maximal independent set of the power graph again. And I just say that all these guys, let's say that they are colored with, what did I choose? 4. Okay. And actually, this is the part where this word complexity comes from. The fact that we're reusing MIS. Now, for every vertex here, sort of in the middle, in this subpath, we just need to find one guy to be responsible for their coloring. That's the idea. That's the whole idea. So, for example, what did I write? Well, let's say that this was index 44, 77, 88. Okay, there's some other stuff here, right? Okay. So this guy will color both this side and that side. That's it. So this is just to give a direction in a certain sense to our path. Yeah. If the path was in a way directed, you can say, okay, then I color the subpath sort of to my right. This is not the case, so we're relying on ID. So, but there's really nothing to this. And now, in the middle here, I will color this with some square-free words, as I claimed before, the one that starts with this, let's say 1, and ends also with 1. Okay. So let's say that here I have something like 1, 2, 3, 1. Here I want something like 1, 2, 3, 1, 3, 2, 1. Okay, there's some 1 here, on. There's some 1 here, 1 here, 1 here, and maybe there's also some 1 here in the middle. Okay. So that's it for now. So what we're going to do next is something a little bit weird, but I'm going to recolor all of this with 1s and the ones with 4s. Okay, you get why we're doing this in a moment. So now let's say that I have some new coloring now. So this 1 next to a 4, it becomes a 4, 1, 4. These that stay in the middle, it stays as 1. Okay. 1, 1, 4, 1, 4. Okay, 2, 3 stay the same. This one is next to a 4, it becomes a 4. The 4 becomes a 1. And 2, 3 stay the same. This one in the middle stays as a 1. And 3, 2, 4, 1, 4. Okay. Right. So we have this weird thing. We will see why it works. And then finally, I introduce some randomness here. In a way, let us try to understand why I even need randomness, right? You can sort of see that this problem, in a way, is very non-local, right? We're talking about square-free words and squares that can be arbitrarily long and can appear anywhere in your word, right? So doing it deterministically doesn't really make sense because it's very hard to check that you didn't create some squares. Okay. I'm not claiming that it's impossible, but this is why, like, naturally, we tend to want to involve randomness. So what are we going to do? So what am I recoloring? In which with 1 gets recolored 4. Okay. So now these ones stays the same, right? Because they are the one in our independent set. And these guys get some, like, flips a coin and maybe it turns to a 4. Flips a coin, maybe it turns to a 4. Did I miss something? Okay, this one, yes. Flips a coin, maybe it turns to a 4. Okay. And this randomness will be useful to avoid long squares. Now, let's first maybe look at the communication complexity of this thing before correctness, just to make sure that we are sort of efficient, right? the first step here, I'm just taking MIS. So again, I'm just multiplying like log n by some known complexity for MIS. I just try to find like the best one that we know. It's always something like this. And then the rest we can do it log n rounds. Yeah. Why is that? Because actually these guys cannot be too big, right? We're talking about MIS here, a maximal independent set. So this thing, its length is like, so first at least like L, there's maybe a +1 here. And it can also not be more than like 2L plus 1. Because if it's too big, you find a vertex in the middle that can be added to your independent set, right? So all these things are actually, you're working in balls of log n here. Okay. Now, since I hope you're convinced that we have an efficient algorithms in some log n, maybe log square n's number of rounds, let's try to see why this works. Okay. So, maybe I can write it over here. But actually, can you read this well? This. Okay. What is the probability that I created a square? So probably there exists a square in my word. It's like at most, say the probability that there exists a short square. Which I mean length at most L, plus probably exists long square. So this. Okay, maybe I still need this in here. All right, so in our algorithm, is it possible to have a short square? Let's think about it. Can this square be like here? Imagine this is my square. Is it possible? Well, it is not, right? It's just because here I chose some square free words, and even though there was some switching 1 to 4 and stuff, this square free words is built on 1 to 3. So switching a 1 to a 4 doesn't do anything. Okay? Now can this square be over here? Like overlapping these things? Well, maybe, yeah. So how can there be a square here? Let me get some space. Well, the square can has to involve somehow these things, right? For this 4, 1, 4 thing. Yeah? Maybe it involves 4, 1. I mean, by involve, I mean like this appears later on. Okay? Or maybe it's the other side. But these has to participate in my square. Yeah? If it's cut off here, then it's only on one side. Okay? But remember that this sort of thing is not possible because this 4 was a 1 before. Yeah. So if you go back in time and you reflip your coin, this must have come from a 1, 1. Since we chose the square free words, this is not possible. Okay? So actually, if you have short squares, meaning that like they touch only either none of these or like only one of these, then it's not possible. Right? So the probability of a short square is actually 0 by construction. And now it is quite clear that the probability of a long square, what we want is for it to be exponentially small. Okay? And we would get the same thing as before. So now, let me try to show this a little bit formally. How do you see that this is exponentially small? Well, this is due to the randomness that we added in the end. Okay, so imagine now this is your super long square. guess I use this color for it. And this is like is the middle. Okay? And on this long square, you have some stuff from your MIS here as well. Okay. So what I want to compute is like the probability of there existing a square of length, something like 2i with these 2i at least. Okay. First observation we can have is if you just take some block like over here, like a very small one, say 4 letters, then each letter in 1, 2, 3 has to appear at least once.
Because there is no square root with more than 2 symbols.
Yes, because say I start with some A, right? I cannot repeat A, so there's some B here. If the third letter does not appear, then this must be an A again, but then I cannot have a B now. Yeah? So C must appear now. Okay. So if I just take a block of 4 letters like this, then I know that one of these A, B, C must be a 1. Yeah? And the 1 had a chance to be flipped to a 4. Okay, this is where my randomness is involved. Okay, so now once we have this very simple observation, then we have that there's some 1/2 here, my coin flip. How many times did I do it? Well, something like I times. Because yeah, what I'm just saying here is that like both sides has to be the same, right? Like I have the same block here, that is A, B, A, C. So what is the chance for both sides to be the same? You just look at it like sort of block by block. Yeah. There's some fixed stuff here, so like a small number of them. So let me just remove it. I don't count it in my random stuff. So there's something like 3i over L. You know. There's I over L for these things, and there's some fixed stuff surrounding them as well. Yeah. There's some fixed stuff here as well, so I just remove that. And then divide this to block of 4, you get something like this. Okay? And now, probability that there exists a long square is at most. So what do I take? Like, it can start from anywhere, I guess. And it can be of any length, at least L, and of this thing. Okay. So this basically for a well-chosen L, which is some constant times log n, is you get like 1 over OEM. Yeah, and again, you want this like to sort of depends on your constant C here, but everything is in the choice of L. Okay. And that's it actually. So we didn't manage to do entropy compression, so we just thought, okay, let's just try to do it without thinking about this entropy compression thing, and we found sort of this ad hoc algorithm for square free words. And just to talk a little bit about what we can do in the future, well, this is still an ongoing work. We think that we can do this with 3 colors, avoiding this 4th one. And we can generalize this for general graphs, basically. So instead of just non-repetitive colorings on the path, just take any graph. Now it will depend on maximum degree, of course. And actually, if you do this sort of entropy compression thing, you're sort of multiplying the number of colors by delta. So in a way, you can get something, just like some results. It might not be very interesting, but we're hoping to get something better. And yes, so our methods also works really well for star coloring, just because this is star coloring is just avoiding a short square. We also thought about acyclic coloring as well. all of these things that forbids patterns on paths, sort of similar, work in similar ways. So yeah, so that was also our initial hope, that we can do this for all of these different types of problems. And there's still this big open question, is that can we really find a good equivalent method to entropy compression for the local model, that yield similar bounds, of course. And thank you very much for your attention.